All right, good afternoon, everyone. Let's get started. Welcome to lecture 4. I hope all of you had a good break. Some quick announcements. So we have extended the homework one deadline until tomorrow 3 p.m. I will send out a message. This is just to make sure you have enough time, to finish the homework because we'll be covering some of the material today. I know some of you have already submitted the homework, so that's great. But with just extra time, about a few hours, about 12 hours or so, so that you can just finish the homework. Then I'll have office hours today until about an hour after the class ends. So please stop by. I have already got to interact with all of you on a one-on-one basis. So please stop by. Feel free to ask questions. Additional to office hours, you're always welcome to email me and email Felipe and copy us so that we can answer your questions. So don't hesitate. Asking questions is always good. So feel free to reach out to us. And then finally, we will have the homework officer. Essentially, you can answer all the questions about homework today at 6:15 p.m. Unfortunately, it's a little late, but this was the only time that worked, avoiding conflicts with the math methods and the RCR code. So that's why 6:15 to 8 p.m. at B331. Felipe will be there. Please feel free to ask questions. And again, we will make use these opportunities to interact with us and ask questions. Just a reminder, because of the last cancellation of the lecture, as I mentioned at the start of the course, we'll have a first makeup lecture on Friday in the same room. We will not take into account the polling and anything for the grades, and we'll also record it as I've been doing for all other lectures. In case you have some other commitments, you understand. We'll have all that information there, and we can always reach out to us again if you have any questions about the lecture. Okay. So these were announcements. Any questions here for homework, office hours, makeup lecture, anything that anyone wants to discuss? All good? All right. Yeah, go ahead, please. So this is just for the homework. Every week he also has on Fridays for 3:30 to 4:30 p.m. Is that correct? Yeah. So Felipe meets every week 3:30 to 4:30 p.m. every Friday. This week, if you want, we can still have them, but I presume many of you won't have questions. The homework will be due tomorrow, but we generally have them every week, and then we'll have an additional office hour just one day before the homework, so that you can answer any questions. Okay. I have 2 office hours both days after lecture for 1 hour. Again, you can just drop by anytime and you can discuss any questions or homework problems. Any other questions? All right. Okay. So let's get started. So today we have a few things to cover. Just quick recap, because we are meeting about a week later. So we have been discussing in the first 3 lectures. We discussed the fluxes. So this is the Fourier's law, where we had the heat flux as the gradient of temperature. Then we discussed the species flux. This is again only the constant flow and pseudo binary. We discussed that there can be other modes, and we will discuss some of them today. Then finally, we also briefly mentioned the shear stress, and we will discuss this more in part 2 of the course. We mentioned Prandtl number, Schmidt number, and Lewis number for relative rates of transport. So hopefully now all of this looks familiar. As you're also solving homework 1, problem 1 and 2, you will see these things come up again and again. Okay. Then in the last last lecture, we finally derived all the equations that you see on the top, which is we have the scalar value, we use control volume, and a flux, general flux, and a volumetric rate of generation, BV, and we derived for 3 different cases. One was the species conservation equation, one was the heat energy conservation equation, and one was the continuity equation of conservation of mass. And just remember that we derived these equations using some assumptions, which was one was constant flow and pseudo binary for the species equation, and constant conductivity for the thermal equation. I again want to emphasize, if you are feeling a little uncomfortable with these derivations, do check out the supplementary videos. We do go about in detail about deriving these equations, in case it's a little bit more confusing to you. Okay. Any questions on the conservation equation derivation? Good. Okay. Then we finally discussed the boundary conditions. Last time we started adding the constant value, which is simply just the value B equal to B naught, B being the scalar here on the left. Then the constant flux, also again given to you, just to take the dot product with the normal vector. And the most important one, I want to really emphasize this for your understanding, is the interfacial balance We discussed that there can be two interface, it can be an interface, phase one, phase two. We define it by the normal to the interface, Ni, and Vi being the velocity of the interface. We discussed that we will discuss a problem today with the velocity of the interface, so it will become clear what that really is. We added that this is the formula that you can use, basically a relative flux, where we subtracted the contribution from the interface velocity in the phase one and phase two, taking a dot with n and then adding a surface generation. Again, we'll see an example of surface generation today as well. So hopefully some of these abstract concepts will become start to see more, you can start to see some practical utility. So this is the equation. This is very important. Please do not forget the normal vector goes from phase one to phase two. This equation will not work if a normal vector is reversed and you'll get the wrong answer. Okay, so make sure you remember the convention that the normal vector for the interface has to go from phase one to phase two for you to use this equation. Okay, don't forget that. And we'll do example for this. Finally, we mentioned that you may need to invoke these additional conditions for temperature being equal or concentrations being different because of a partition coefficient across the interface if you're solving in both interface. We won't be doing this today, but you will be doing this in your homework 2 problem, something like this. Okay, so this will also become more clear. Any questions on boundary conditions? Anything that was unclear? All right. Okay. So now let's go forward and start the class from where we ended. This was the problem we ended last week, where you did actually already. I'm not going to poll again. And the question really was that we have a liquid, like a sort of a tube of liquid where two gases are exposed. The concentration inside the liquid phase of these gases are given at the x is equal to 0. The system is 1D steady, constant density, no convection, and pseudo binary. And the question was, what are the governing equations for species A and B? Okay. So before even going further, how many species are there in the problem total? 2. Does anybody disagree with that? Is it not just 2, or we can move? There's the solvent, right? So don't forget there is also a solvent. So I want to clarify this because this is, it's okay. You can see it's actually for practical purposes just 2 species. So all of you are right, but reality there is also a solvent, but we don't care about the solvent because we have said the system is pseudo binary. Okay, so just note that term pseudo binary clarifies that we are thinking of CA and CB, and that's why I'm saying diffusivity of A, diffusivity of B. There's actually diffusivity of A in the solvent, diffusivity of B in the solvent. So A and B are dissolved gases, but there is a solvent which is just not solved for the solvent, but there is a solvent. So in total there are 3 species, but we really are interested in the 2 species which are A and B. Okay, so it's implied in the problem that there is a solvent. Just to clarify this, as you will see, always remember that you need to make sure that the system is pseudo binary for us to be able to use the equations which we were seeing here. Okay, so this is the equation we were seeing. All right. By the way, before I should just mention this. So now we have moved on to chapter 3 of DEAN. So this is chapter 3 of DEAN, and here we will be learning about 1D steady problems. So the idea is we have the conservation equations, we have the boundary conditions. What are the simplest scenarios we can solve? Okay, so we don't want to complicate. It's obviously a 3-dimensional time-dependent equation. All these equations that you see on the top. So we want to solve 1D steady problems, which are steady 1D. So it's the simplest problem, and that's what we'll start. In the next lecture on Friday, we will become approximately 1D steady problems. We'll start to complicate this as we go along, but the first step is 1D steady problems, and that's what this problem is about. Okay, so pseudo binary, we could use that equation, and as I had mentioned, the correct answer is actually C. So it's not difficult for all of you to see that this is, we can expect this term, but the main idea here is that there is no reaction in the volume. It's a surface reaction. So whenever we are thinking about the equation here, remember that this term is actually a surface reaction. So this is actually a volumetric reaction. Okay, volumetric generation term. Okay, volumetric generation term, generation. And so that's why we cannot use Ri there because it's a volumetric generation term. And in the tube, the reaction is really just happening at the surface. Okay, so the surface, the reaction is happening at the surface. So we cannot really have any volumetric reactions coming in. It's just simply the diffusion. That's what it is. Okay, makes sense. Any questions here? So you cannot have. So I hope this is clear. Just want to emphasize this again. That when we wrote this equation, we were writing for a per unit volume basis. So if I had a volumetric reaction, basically everywhere in the tube, I would have that term. But now it's only at the surface. So we cannot have it for the entire volume because it's actually just happening at the surface. Okay. So you hopefully this will become clear as I elaborate on this further. Okay. So let's just mention this. So this was lecture 3, question 4. It's C because no volumetric reaction. So we have Ri to be 0. So and d square Cb by dx square is equal to 0. Okay. All right. So now let's just start quickly thinking about this problem. So we have now the governing equation. So let me remove this. Okay. So we have the governing equation. Now we will be thinking about the boundary conditions. Okay. So let's start. Hopefully this is an easy problem. So what do you think will be the boundary condition at x is equal to 0? So let's start the poll. This is just to get you started. So we'll just do a 45-second poll. Hopefully in another yeah. So we should all see this on your screens. Let's just do 45 seconds. Quickly we'll finish the poll. So what do you think is the boundary condition at x is equal to 0? All right, another last 10 seconds. So please get your answers in. I'll finish the poll in another 5 seconds. Anybody last one wants to get in? All right, let's stop and let's look at the answers. So all of you did get it. Almost all of you did get it right. It is the first one, simply, which is the given concentrations. Okay, so it's a constant value. Simply we have C is equal to C naught and C is equal to 0. Now note again a word just so that you are able to kind of see this through. This is the concentration inside the liquid phase. If in your exam or in a problem I says give you concentration outside, then you have to multiply with the partition coefficient to get the value inside. Okay, this is the concentration of the species inside, right? So for instance, imagine this Ca is carbon dioxide, right? And Cd is nitrogen, right? And I can give you some values of concentrations of carbon dioxide and nitrogen outside. Then I can give you a partition coefficient on how they will basically partition so that you can get the concentrations inside. Okay, so in this case, it was simply given to you, but you may have to adjust that in case you are given the values outside. Okay, I hope that's clear. Any questions on this problem? All good. Okay, so now let's do the next problem, which is what is the boundary condition at x is equal to L, and I will give you 2 minutes to do this problem. You can let's just start this. This is a more complex problem, so hopefully this will start soon. So let's do 2 minutes. Take your time, and I would say you can even talk to your neighbors while you're doing this. Okay, so you can start talking now if you would like, or you can talk whenever you would like. So take your time. This is an important problem. We'll do this together, but feel free to talk to each other as you do this. Maybe last 30 seconds. You can continue to discuss it, but get your answers in. All right, I will close the poll now. So if you haven't done your answers, then please do submit your answers. All right, I'll close the poll now. All right, let's look at the results. So we have some distribution, but more towards B and less towards C and some towards A as well. And all of the answers are actually okay. So if you're getting confused a little bit, that's all right. We haven't covered this material. Okay. So the correct answer. So if you're thinking along, I presume some of you who did select A thought it's an impermeable surface. So I should have the flux to be 0. And B and C are basically sign flipped. So we'll see the correct answer we'll calculate is B. Okay. So most of you did get it right, and you will solve it. But as you will see, this is the difference between our undergrad courses and maybe grad courses, that these interfacial boundary conditions are where all the difference will happen. Okay. So some of you had selected when we did the first problem in governing equations, the reaction was going in your governing equations. We saw that there was no reaction in the governing equation, but now the reaction is with the boundary condition. Okay. So we'll derive how. The correct answer is B. So let's do that now. And let's hopefully this is an instructive problem, and I really like this problem because it really clarifies. Sorry, let's me go back here and move here. All right. So let's try to do the boundary conditions. So we did do the boundary condition for Q1. That was simple. That we said it's A, CA at x is equal to 0 is CA naught, and CB at x is equal to 0 is equal to 0. All right. Now let's do the boundary condition at the other end. All right. There is a reaction of A going to B. The reaction constant Ks, the order of the reaction is 0. Okay. And we have to find the boundary condition, and this is being given as impermeable surface. Right. So clearly this is an interfacial system, right? There's something which is happening at the system. You're not given a flux. Okay. It's not constant value because you're not given a value. It's not constant flux because you're not given a flux, right? So it's clearly an interfacial boundary condition. So let's start first there. So we'll say F minus BVI dotted with N cap 1 minus F minus BVI 2 dotted with N cap plus BS is equal to 0. And this is X equal to 0, right? So, sorry, this is the direction of X minus 2. All right, X is equal to 0 and X is equal to L. All right. So my interface is here. If I choose my N or N cap, I mean, I sometimes use an interchangeable. Ideally, it should be N cap in the X direction. Then which should be the phase 1? It should be this one. Okay, phase 1 and 2. Just remember that if I choose my Ni, let's just make it Ni so that it's not confusing. Ni to be Ex, then Ni always has to point from phase 1 to phase 2. If some of you want to really try this, I would encourage you to do the Ni to be minus Ex. You will still get the same answer. In that case, The phase one will be the one here, phase two will be the one. Okay? So you can try either way, it should give you the same answer. So for convenience, we just choose the positive one. It's Ex, phase one and two. Okay. Now the interface is clearly it's a cube, interface is not moving. Very obvious in this problem. Interface is not moving, so we can get this term away. And then we have this. Now, what is phase two? Phase one is inside the tube. Here, phase one is this one. What is the flux outside in phase two? Zero, because it's an impermeable surface, right? You have been given that nothing can go beyond that surface, right? So phase two, the flux is zero. All right, so this goes to zero. So basically, we get F1 dot n plus Bs is equal to zero. So F1 dot n plus Bs is equal to zero. Okay. And basically, this is because n is Ex. This is becomes flux in the x direction. This is essentially Fx plus Bs is equal to 0. Now there is no convection. So remember again, no convection. So it means that minus dA del dCA by dx is the only flux I have because it's a only diffusive flux because it's pseudo binary. So I can write it like this. There is no convection. I can write it like this. And what is Bs? Should it be plus Ks or minus Ks? Minus Ks, right? Because we say Bs is surface generation, but Ks is being reacted. So it's minus Ks. And I don't have any multiplication with the rate like Ca square because it's a zeroth order reaction. Okay. In just a minute, we'll do a first order reaction, in which case we'll have a Ca, something like that. So just a reaction with Ks is equal to 0, or it implies that dCA by dx at x is equal to L is, or minus raised to 0, this minus Ks. Okay. And so I encourage you to do with the B as well, in which case you will get a plus Ks here and Cp and dB, and you will get the answer to be B. Okay, that answer to be B. So can somebody convince me without solving that the answer is B? Without doing any math, can you figure out a way and show that this should be only B? It cannot be C or B should be no, it cannot be A. Because so how do you think we can convince ourselves that it should be B? Physically. Right. Absolutely, yeah, absolutely. Perfect answer, right? So you see all of you see that point that if I'm working on X, I should expect the concentration to decrease because like I should expect the concentration to decrease because I am reacting to it. I shouldn't expect the concentration to increase. So this is very clearly this del C by del X, dC by dx should be negative. Right? Otherwise, I am making it rather than reacting. So this is another physical way to check your sign. Some students like physical intuition, some students like mathematical rigor. So it's up to you, but you can see this also here. That physically, it makes sense. So you can reason out that, well, I cannot have concentration of A to be increasing if I'm reacting. So it should be. That's another way to look at it. Yes, please, Mike. Oh, sorry, maybe this was not clear, but here we say no convection in the problem. So we cannot have any convective flux. Right? So if, yeah, go ahead. Sure. Great question. Yeah, so the flux in the x direction would also have a convective component. So you will have a concentration A times velocity. So you need to know the velocity. In general, as you can imagine, it's unlikely to have any normal velocity component to a solid wall. So generally, I would say convective flux is equal to 0, but let's say if it's a flexible interface or some other problem, you can have a convective flux at the interface. Generally, it's mostly diffusive, but you can have maybe some scenario. Yes, So which term did I cancel? Yeah, so the VI, because VI is zero, right? So the interface of the velocity is zero. It's a solid ball. So VI I can cancel, right? And I cancel the flux in the second phase because it's an impermeable surface and I cannot get any flux on the other side. Defined surface. Yeah, great, please. Great questions. Any other questions? All of these are great questions. So this is really good. I would encourage all of you, the way you are asking questions now, to actually keep asking these questions while you're solving these kinds of problems at home. Because that is how you will kind of learn this development process of writing the correct boundary condition. This is excellent. And I really strongly encourage you to kind of ask this question. I even do it today. Okay. So whenever I'm setting up the problem, I'm doing the lecture preparation, asking these signs, why not convection, why not, like, these questions are what will make your understanding strong. So great questions. So basically now you saw that we have two boundary conditions. One is dA dx is equal to minus ks. We have one boundary condition for A, B, and one for B. We have two boundary conditions and we have the equations, right? So you can solve the problem mathematically. This will not do this in the class, but if you're interested, you can do it at home. You can solve this problem and you'll get a concentration profile for A and B and the entire field. All right. All right. So let's keep going further. Now let me switch around the problem and let's do now volumetric reaction. Okay. Just a quick note, I have flipped sign of x is equal to 0 and I will use this for convenience. I will see later. So hopefully this problem is, you would be able to do it. Let's do a poll. I'll give about a minute for this one. So it's a similar problem, but now we have a volumetric reaction and we want to find the governing equations for A and B. I don't think you have seen the, now you should be able to see it. So let's get your answers in. Let's do about a minute or so. What is the right governing equations for A? Maybe another last 15 seconds to get your answers in. All right, I'll close the poll in 5 seconds. So some of these have still not responded. All right, let's end this now. Let's look at the answers. Great, most of you did get it correct. The answer is B. So there are two differences with the last problem. Is that it's first, it's a volumetric reaction, so it will go towards the in the governing equations. It will come, it's a volumetric reaction. Also, it's a first order reaction. It's not a zero order reaction. That's why you have a KCA. Okay. So great, and minus for A because it's being consumed, plus for B because it's being generated. Again, remember that RA and RB are kept equal. Oh, this one here. Oh yeah, let's discuss this. Yeah, good question, Noah. So let's come here. So let's start from here. This is our governing equation, right? So let's now go more step by step. It's steady, so this goes away. There's no convection, this goes away. And so Noah's question, why the second derivative? Because it's a Laplacian. So the governing equation itself is a Laplacian. Laplacian is del square by del x square plus del square by del y square plus del square by del z square on CA. Okay, and it's a 1D problem, so I'll simply get dA d square CA by dx square, and then all of you had it correct. It should be great question. So the first, so who asked the question? Yeah. So that was because it was a boundary condition. So good question. So again, you're all thinking along the right direction. So So here the reaction came to the boundary condition, and I had a flux, and flux are defined through the flux laws, right? These laws here, which have first derivative. So when you're writing the conservation equation, that's where the second derivative has come. See that point? So that's why you have the first derivative, because you were thinking of the boundary condition, and boundary conditions have fluxes, which are the first derivative. And now I'm not thinking about, right now I was just thinking about the conservation equation, and which have the second derivative. Okay, so that's why you have the second derivative. So I hope that's clear. Okay. Yeah. Yeah. Oh, sorry. This one, yeah, yeah. Connection, no connection. Correct. V is zero. No connection means V is zero. And again, I can use this equation, by the way, just so that I emphasize, we can use this equation because it's a pseudo-binary system. I can't even use this equation if it's not pseudo-binary. Why is it in the second line? Why is it so this should be CA, my mistake. This should be CA. Oh, it's a typo, yeah. It's a CB here. My mistake, it's a CB. Yeah. Yes. I think I probably did write it. We will clarify this always in general. I probably forgot to mention, it should have mentioned. So apologies for that. This problem should have stated that this is a no convection. Good question. It's fine. It's something I. Yeah, we generally stated to have like in general, I would say for part one of the course, you will never have like a purely like a velocity profile or anything like that. You can have some convective flux, as you will see in one of the example problems, but we'll never have like a velocity profile where you will separately evaluating velocity and density. We'll have it in the second part and the third part. Yes. Mass, absolutely. So no, I hit the point that when you say convection is zero, we mean the velocity, which is the mass average velocity zero. You can still have the molar average velocity to be non-zero. So that's where we will get to in the next example, and I'll clarify that. A great question, great operation on this. It's basically when the mass average velocity is zero, it's when you say convection is absent, but the molar average velocity may not be. We will see an example of that today. And that's also the homework one problem. Any other questions here? All good. All right. Let's keep going. So great. I really like the questions here. Please, keep asking questions. It's awesome. So we get this as the governing equations. Again, always remember, first step, governing equations. The second step is boundary conditions. Second step is boundary conditions. So I'm not going to spend too much time here because we did cover these boundary conditions more or less. So with a slight difference. So first thing is, I just want to know that x is equal to 0 and x is equal to L are flipped here. This problem is out of just convenience. It doesn't have to be this way. I just designed it. And the book also has example on this like this. So CA at x is equal to 0. So let's start with x is equal to L. CA at x is equal to L is CA naught. CB at x is equal to L is 0. So same as the last one. So constant value. And in this problem, there is no surface reaction. There is nothing on the other side, just impermeable, right? So if we go to the problem, it says here it's an impermeable surface here, like this system here. Maybe I should have mentioned that also more explicitly, but essentially this sort of like surface is impermeable. You cannot have anything going through the surface, and there is no reaction on that surface. So it simply means that the flux is 0. So on the other side, we'll get dCA by dx, dCV by dx, and x is equal to, so gradient is 0. If you are confused and you are more comfortable with the surface reaction, you can think that surface reaction rates are 0, AS is 0, will also give you the flux is 0. Any questions here? So this is typically what you would always do in your problems. Okay, governing equations, boundary conditions. You want to have the governing equations, conservation equations. Look at the assumptions. If they satisfy, use the table. Then go to the boundary conditions. Either there will be constant value, constant flux like this, or you may have an interfacial boundary condition like the last problem we were doing, where you will have a little bit more work to do, but you will be able to find the boundary condition. This is absolutely the more critical part of transport and not the solving part which you will do in a minute. Okay? So this is the important space.
So we have the same boundary conditions.
Absolutely, yeah. Again, excellent question. So if you do that here, you can imagine now my P is equal to 0. There is no generation of the surface, right? This is flux is 0, so you get F1 dot n is equal to 0, or Fx is equal to 0, or dc by dt. Generation term. So interfacial boundary condition can always be used for a flux condition, but it's just that you can directly write it as well. You can do it either way. Any questions? All right. Okay. So let's go further. So now what I want to do, this is for practice, you get more and more used to this. This is the governing equations and boundary conditions. Let's focus on CA. Okay. So we are focusing on CA. And what I want you to do is non-dimensionalize the problem on your own. So you have been given how will you scale, use this transformation, define theta as CA by CA naught and x tilde by x by L, and find this expression of dA, which is known as a damp polar number. Okay, so I'll give you a couple of minutes and let's start this poll. What is the expression of dA? Find the expression of dA and using the equation, which is the equation for CA, transform the governing equation for CA and find a damp polar number expression. All right, I'll give a last maybe 30, let's say 30 seconds, and then end the poll. Please to get your answers in. And hopefully this will, I don't know if you have been doing this enough in your math methods course, but hopefully there is some synergy with the kind of changing variables and so on. All right, I'll end the poll now. So let's look at the results. So good. So many of you did get it right. That's not, you did not. That's all right. The correct answer is B. Damp polar number comes out to be L squared by dA. So we'll do the derivation, but I just want to emphasize another way to look at this is if you know the dimensions of the problem. So a rate constant, a first order rate constant is second inverse. Okay, so let's go here. So just quick note. So we're doing d squared theta is equal to minus dA theta, and we'll derive this, but dA came out to be kV. I was saying it will come out to be this. So like 4Q4, the answer is B. One way to think about is this the units of this is second inverse. The units of these are meter square, and dA is meter square by second. So this is the only one that will be dimensionless in the data. This is just another way, but let's derive this from the equation we have from here. So some of you may have just done it automatically. You may have done this equations in the past, but you may not have seen this. But a formal method, if you're not as comfortable, is think of it like this. dCA by dx, I'll just do it once, and then I want you to just practice this yourself, is d so you can do like this, dCA by d theta into d theta by dx, and dCA by, and we know that CA is equal to CA naught theta, right? I hope all of you can see this is just, I'm just multiplying, I'm just doing a chain rule, right? dCA by dx is dCA by d theta into d theta by dx. So this will become, and dCA by d theta is CA naught. So this becomes CA naught d theta by dx, okay? And you can also do this CA naught d theta by dx tilde and dx tilde by dx. I know that x tilde is x by L. So dx tilde by dx is equal to 1 by L. So I'll get CA naught by L d theta by dx tilde. This is a more formal method. Other ways is to say that this is all constant. I can just take it like I'm just changing the dimensions here. So you can just take them out of the derivatives. That is also another way. And finally, you will do another derivative. Let's just not rush this. I want to show you the method. Don't worry if you're not as comfortable with this, you will become comfortable with time. But I hope some of this chain rule was done in your math methods, and this will go along with that. I'll just write this here. I just want to show. Okay, so what I'm doing is I'm saying that that is dCA by dx. The second derivative, which is in my governing equation, is actually derivative of dCA by dx of this. dCA by dx from the previous step is CA naught by L d theta by dx tilde, and then you can do another derivation again, another change to that. Okay. I mean, it's like it's all constant, so you can simply see that CA naught times theta will become CA, and L square times x tilde square will become x square. That is another way to think of the second derivative of CA respect to x. Okay. So does that make sense, or it's unclear? Any questions at this step? I know this is a little, we are going a little faster, but I hope you've seen this before. But if not, please do practice this. So once you do this, we can say dA d square CA by dx square is equal to KBC. This was our equation. Now I'll use this, substitute this here to say dA CA naught by L square d square theta naught by theta by dx tilde square is equal to KV CA naught theta. This is the value of CA. This will get cancelled. I'll get d square theta by dx tilde square is equal to KV L square by dA theta. And this is my Damn-Coulomb number. This is my Damn-Coulomb number. Okay, so this is another way to come to the same answer. It's a little long, but again, a more formal method. This can help if you have many variables which are functions of time and so on, just to kind of see the whole process. Okay, don't worry, again, it's not something you will get used to this with time. Second homework will have plenty of such derivations, and you make sure you have enough practice of this to kind of get used to sort of coming up with this. And with time, actually, you don't have to take this much effort. You can see like, okay, you can pull out these numbers and see sort of fraction. But again, if you're uncomfortable, don't worry. I will say spend 30 minutes at home this time and I'll make sure you're comfortable with this and you will get this point. Now we have this equation now. So again, this is our governing equation and our boundary condition would now become theta del theta by dx at x is equal to 0 is equal to 0 and theta at x is equal to 1 is 1 because it was Ca by Ca naught, right? Concentration becomes Ca naught at x equal to L, is x theta equal to 1. And that's the two boundary conditions, and this is the governing equation. Okay. So before I give you a 5-minute break, how would you solve this equation? Does anybody have you already done this in mathematics? We've done this in mathematics, like if you have a second order differential equation with the same, if you have like a t square over dx square is equal to y, you have linear functions of exponentials plus exponential or linear functions of sine hyperbolic and cos hyperbolic. Again, in my opinion, like you will get used to these things in practice. The more important part is setting up this, not about solving this. Okay, so I'll give you the result at this point. You can. It's not important to sort of worry about solving this, but this is what you will get as the result, and we will discuss this after the break. So it's 12:51. Let's resume at 12:55. Okay. In the meantime, please feel free to come here and ask me questions. We'll resume at 12:55 because I do want to get to the next problem, which is very important for your homework on problem 3. Okay. So let's take a break and we'll resume at